Okay. My warm-up questions are just to review what is U substitution and what is integration by parts. So how about we look at one each of those problems. So U substitution. That was the easier case, U substitution. And when we did U substitution, you were given an integral within which you could identify a U term as well as the derivative of a U term. So for instance, a basic U substitution problem you might have would be like x cubed plus 6 to the power of 5. And if we're going to claim that that's our U, what other term would we need to see sitting right next to it? Yeah, the derivative of x cubed plus 6, which is 3x squared, but it really just has to contain the x squared. So I would also need an x squared term right there. So this would be a great example of U substitution. You have to identify a part of this integral that could be your U, and we're going to call that our U right there. And you also have to identify the derivative of U, which would be 3x squared. The x squared term also has to be in there somewhere. So this is definitely a U substitution problem. So we would go ahead and say that, I'll do it down below, that U is x cubed plus 6, and then du would be 3x squared dx. And I move the 3 back over to the other side, so 1/3 du is equal to x squared dx. And now I have all my components within the integral. So I could actually call that what? I replace the x cubed plus 6 with a u, so that's u to the 5th. And then I replace the dx and the x squared with a 1/3 du. And that's the integral that we can solve. It's very simple. There's no inner parts. In fact, I'll go ahead and move the 1/3 outside. So it's 1/3 of the integral u to the 5th du. And what is the anti-power rule? We're going to use it quite a bit today. How do you do the anti-power rule? You add 1 to the power and then divide by that power. So this would really be, so u to the 6th, 1/6. And I have to keep my 1/3 there. And so our final answer is 1/18 u to the 6th. Well, that's not our final answer. What's the last thing you do? Go back to the original variable. So it'd be 1/18 of x cubed plus 6 to the 6th. And how do we check if that's right or wrong? You can take the derivative, which we can do pretty simply. 6 times 1/18 is a 1/3. And then you leave the inside alone, but then you multiply by the derivative of the inside, which is 3x squared. And the 3 times the 1/3 cancels out. And you just have x squared outside, which is what we expect. Okay, so that's U substitution. On your paper now, where do we have space to do this? Because I want to do 5 and 6 with you, but I'd also like to review. Actually, can we just do it at the bottom of page 7? There's a lot of space down there. Sorry.
We're not doing 7. So
we're not doing 7, yeah. Yeah, okay, so let's do it on that page right there. And so my review for you of integration by parts is the classic problem of finding the integral of natural log of x. So that will be our review for integration by parts. Because this formula is well worth memorizing. Just like we have all sorts of other formulas that we memorize, this one is worth memorizing. And so we're going to do the integral of the natural log of x. It looks like a pretty simple problem because we already know how to do the derivative of the natural log of x. The derivative of the natural log of x is simply what? Just 1 over x. So we'd like to know, well, what's the integral of natural log of x? Well, we can't do U substitution because if you tried U substitution, I'll just try it over here. Like, let's say that I said that U was natural log of x. The derivative of u would be du equals 1 over x dx. But we don't see those parts and pieces over here. So U substitution won't work. I've got my natural log of x right there. And I've got a dx right there. But there's no 1 over x in there. So you can't do U substitution. It won't work. On the other hand, you could do integration by parts. So remember when we do integration by parts, we're going to make a box. One part will be our u. One part will be our v. And we need to find a u term, and we need to find a dv term. Our u term should be something that we will then take the derivative of, and it should become simpler. And our dv term will be something that we're going to take the antiderivative of. And we hope that it's at least not worse. But even if it did get a little worse, that's okay. Our key thing is that the u has to get simpler. So what should our choice of u be? The only thing that's here, natural log of x. And if we choose that to be u, then our derivative of u certainly is easier. It's just 1 over x dx. Then what would our choice of dv be? The only other thing that's up there is dx, so we just say dv is dx. And what's the antiderivative of dv equals dx? When you take the derivative of x, you get dx. So the antiderivative of dx is just x. And the antiderivative of dv is just v. So we just get v equals x. So far so good. We made choices for u and v. They were simple to calculate. So now we write down the formula. And what was the formula? The formula for integration by parts? Yeah, it was u dv, because of course those are the two choices we made up front. So we're calling that u dv is equal to uv, yeah, then minus the integral of the opposite, which is v du. Very good. And the exciting part here is that we really already did all the work, didn't we? We did half of the work. We had to come up with our u and our v and do the derivative and the antiderivative. But now we just have these parts and pieces that we plug in the formula. So for my original, it's u dv, which is indeed the original integral we're trying to calculate. And then we multiply u times v, so that's natural log of x times x. I encourage us all to write x natural log of x. You wouldn't want to write natural log of x times x, because that's rather confusing. Are both of those x's inside the natural log, or just one of them? So we put the x in front of the natural log of x. And then we subtract the integral of v, which is simply x, and du, which is 1 over x. How convenient. This is wonderful. This right now is when we really know that we did it correctly, because this last integral needs to be easier to do than the first integral that you were given. And indeed, this integral is much easier to do, because it's just the integral of 1. And the antiderivative of 1 is just x. So sure enough, we found the integral of the natural log of x, which is x times the natural log of x minus x. That might look like a funny formula. It's certainly not as elegant, is it? In terms of elegance, when you take the derivative of natural log of x, the answer is just 1 over x. And you're like, ah, that's nice. Whereas when you take the integral of natural log of x, you get x natural log of x minus x, which, is not quite as elegant. In fact, it got worse, didn't it? When you take the derivative of natural log of x, it gets better. When you take the integral of natural log of x, it actually kind of gets worse. You could rewrite it as x outside of natural log of x minus 1, but I don't think anybody does that. So there we have it. And now I want us all to memorize that now. I want us all to memorize that because we are going to use it in number 6, I think. Yeah, we are. That the integral of natural log of x is just x natural log of x minus x. So write it down somewhere nice. Where should we write it? I'm going to write it up here. Big star, integral of natural log of x is actually x natural log of x minus x. We are going to use that formula today. Okay, how does everybody feel about this? U substitution and integration by parts. Did anyone go to the Around the World yesterday? It was pretty amazing. Around the World was yesterday at like 11:30, and it was free food out on the mall. Is that called the mall? The amphitheater? Yeah, they call it Okay, amphitheater. Anyway, they had foods from tons of different countries. They probably had at least 15 different booths with food from Africa, Middle East, Asia, the Caribbean. Oh, I couldn't eat enough. Yeah, I was actually upset when I left because I wasn't able to eat everything. I was already full. That's a very upsetting situation to be in, that you can't eat more. Anyway, it's super fun. Well, just so you know, because Carmen's not here yet, I saw Carmen yesterday, and I really razzed her about the fact that she got to Around the World on time. but she doesn't get to class on time, so when she gets here today, I'll have to say something to her. Okay, so that was our review problem of integration by parts. So now let's go ahead and do these last two. I think you will find number 5 to be refreshingly simple, and number 6 will be a little challenging but fun because we get to use this formula in our work. So here we go. Integration by parts for the integral of natural log of z, the square root of z to the 19th dz. One thing I'd like to say about this problem is that at first glance, when you just look at it, how do you feel? Yeah, thank you, Clarissa. You're like, oh, no. Right? Some things can look challenging at face value. But in times like that, what you need to do is just put faith and trust in the system of how this works. So, what's that? Okay. So we have two components, obviously, and let's rewrite them real quick. We've got natural log of z, and we also have z to the what? Z to the 19/2. So that's the integral we're taking. And let's make our box and think about what we want to do. We've got u and v. We have to choose a u, and we have to choose a dv. What we know for sure is that we want our u to get better by taking the derivative. And we want our dv to not get too worse when you do the antiderivative. So let's go ahead and consider both of these. You know, let's say that u is natural log. That's not a bad choice because the derivative of natural log is just 1 over z, and that's better. And if we chose z to the 19/2 as dv, well, the antiderivative, you just do the anti-power rule. So you'd add 1 and then divide by the number. At least that's not worse. It's still just z to the, what, 21/2 with a number up front? Whereas let's consider the opposite. What if we had chosen for u? What if we chose for u this one? Then surely taking the derivative of z to the 19/2 would get better. It'd be 19/2 out front times z to the 17/2. But what if we chose natural log to be dv? What's the integral of natural log? Yeah, that thing. So if we were to choose natural log to go here, then v would be equal to z natural log z minus z. And that is considerably worse, right? So in terms of our two choices, what's our obvious choice for u? Definitely natural log of z. Could have chosen natural log of z to be here because we actually do know the antiderivative of it now. We have a formula for it. So we could have done it, but let's not. So now we have du equals 1 over z dz. And then for dv, we're choosing z to the 19/2 dz. And so the antiderivative of z to the 19/2 is what? Yeah, so z to the 19/2 plus 1, so that's we're adding 2 over 2, so that's z to the 21/2. But then we divide by 21/2, and dividing by 21/2 is really multiplying by 2/21. Yeah, super. And that's it. All right, so now we go and write down our formula. And the formula was u dv, because those are the choices we made first. And then uv minus the integral of v du. Yeah, Thomas, you got the packets are over there for today, but we're actually working on the one from Tuesday, which you poor man, you did not get to receive. So here it is. You can open up to number, what is this, number 5? You gonna sit right here, Thomas? Yeah. Fortunately for you, Thomas, the whole class is on video, so you'll be able to watch it and go back. Alrighty. Okay, so folks, now let's plug everything in. So we've got the integral of u dv, which is indeed natural log of z times z to the 19 halves dz, which is indeed the original problem. And then we'll do u times v. So folks, should we write down natural log of z times this or put this in front? Let's put this in front. That's natural to have the coefficient out front and then the variable z to the 21 halves and then putting natural log of z at the end. Natural log of z should always go at the end. All right, and then we're doing the integral of v du. So v is 2/21 z to the 21 halves. And then du, which is 1/z dz. Is this integral better? Mm-hmm. Definitely it's better. It doesn't have a natural log in it. It's simply in terms of the variable z. And the 1/z is actually helping us out because it's going to reduce the exponent a little bit. So what's z to the 21 halves times 1/z? Oops.
Would it be like h of the...
Yeah, z to the 19 halves. Easy. And just to be clear about why that's so, we have z to the 21 halves times z to the -1. And so you're doing 21 halves minus 1, which is really 21 halves minus 2 halves. And so indeed, that's 19 halves. And I brought my coefficient, the 2/21 out front. So I've got my 2/21 z to the 21 halves, natural log of z, minus this figure. And so now we just do the antiderivative of that. So I've got 2/21 z to the 21 halves, natural log of z, minus 2/21 times the antiderivative, which is what? You add 1, which is adding the 2 halves back, and then divide by the resulting integral, which is 2/21. Dividing by 2/21 is the same as multiplying by 2/21. And that's it. Right, we're done with the integral. So now it's just a matter of cleaning everything up and making it look nice. What do you notice we can do in this scenario? You can't cancel anything, but you can factor. Yeah, what can we factor? We can factor a 2/21. We can factor a z to the 21 halves. So we can bring out in front 2/21 z 21 halves. And then what's left is what? Natural log of z minus 2/21. Did we do that correctly? Is that what we're able to factor out? I think so. Now, I have been remiss that I have not been writing what at the end of every integral? Plus c. Someone was just talking to me before class about a bunch of problems that they typed in as answers in Math AS, but they didn't take any of them. Did you put plus c at the end?
They already have plus c.
Oh, the plus c is already over there? Okay.
Yeah.
Okay. All right. Well, folks, nicely done. This is a solid, good calculus problem. And so, yep. Any questions about it? So we'll go ahead and do one more. Not use substitution. Integration by parts. We'll go ahead and do this one, the 7x over 3x plus 5. Oh boy, I don't want to erase that. But that's not a lot of good space. I'll do it way over here.
Bless you.
Bless you. So number 6, we're taking the integral of 7x over 3x plus 5. So what should be our choice for u and v? Oh, that's dv. What do we even have up there? What are the two functions that we see up there? I mean, there seems to be an obvious choice, which is we have a numerator and we have a denominator. But does that mean that one of our choices would be 7x and the other choice would be 3x plus 5?
No.
No. Why not?
Because,
Well, yeah, you also have the dx in there.
well, because you're, like, it's all kind of part of one, so you could do 7x, but the other one would have to be 1 over 3x.
Yeah, exactly. We need to make our choice for u and dv that will completely capture all the structure in the formula. And the fact that it's a fraction has to be captured in one of our choices for u or dv. We can't just choose the numerator to be u and the denominator to be dv and then plug things into a fraction. We have to capture the entire formula in there somehow. So which one should we use where? Keeping in mind that we want the derivative of u to be simpler and the antiderivative to be at least not worse.
You could use 7x.
Yeah, ultimately you just try them both and you see what happens. If I try 7x for u, then the derivative is definitely better. Du equals 7 dx. And if I choose 1 over 3x plus 5 for the dv, what's the antiderivative of 1 over 3x plus 5?
1 over 3x.
Yeah, the antiderivative is actually the natural log of 3x plus 5. And just to show that to you, if you had the natural log of 3x plus 5 and you wanted to take the derivative of it, what would it be? The derivative of natural log is always 1 over the argument, right? So the derivative of natural log of 3x plus 5 would be 1 over 3x plus 5. However, this is the chain rule. So you'd also have to multiply by the derivative of the inside function. What's the derivative of the inside function? Just 3. So you'd also have to multiply by 3. So if you take the derivative of natural log of 3x plus 5, you get 1 over 3x plus 5 times a constant. And so if we want to go backwards, from 1 over 3x plus 5 and take the antiderivative. First of all, I need to get rid of that 3, don't I? If I move that 3 over to here, then I would have 1 over 3x plus 5. And that is the derivative of 1/3 natural log of 3x plus 5. Is that fair? Does everybody believe it? That the derivative of 1/3 natural log of 3x plus 5 is 1 over 3x plus 5? And we want to do the antiderivative of 1 over 3x plus 5? So the antiderivative of 1 over 3x plus 5 would be b equals 1/3 natural log 3x plus 5. Now I realize we've been saying things like when you take the derivative of u, you want it to be simpler, and when you take the antiderivative of dv, you want it to be not worse. Well, again, we can be a little flexible with the not worse part, because at least it was something. You know, this is a real formula. The 1 over 3x plus 5 became natural log, and that's its own thing. So I think this was a good choice. And just to convince you that it was a good choice, imagine had we done otherwise. What if we had chosen for u 1 over 3x plus 5? And if we had chosen for dv 7x? Well, what's the derivative of 1 over 3x plus 5? You'd have to do ho-de-hi minus hi-de-ho or ho-ho. Or you could have just called this 3x plus 5 to the negative 1. In which case you'd have to do the power rule, add 1 to the exponent. Oh, no, you can't. Wait. No, the derivative. You bring it down, negative 1, 3x plus 5, and then you subtract 1 from the exponent, which is negative 2. So really, this is negative 1 over 3x plus 5 squared.
Is that the power rule and the chain rule?
Oh, yeah, and the chain rule, so you'd have to multiply. So that's squared. And then times 3, so that's times 3. That's definitively worse. We would have gone from 1 over 3x plus 5 to negative 3 over 3x plus 5 squared. And over here, the antiderivative would have been okay. It would have been 7/2 x squared. Could we have done it this way? Sure, we could have done it this way. But in our final integral of v du, if you look at v du, it's now worse. If we did it that way, this integral would have been worse at the end, and we would have been worse off than how we started. So we definitely don't want to do that, and we definitely made the right choice right up front. Okay, so let's go for it. We already made our choice, so we're going to replace everything. 7x becomes, we're writing down the formula. U dv equals uv minus integral of v du. By the way, Thomas, that's the formula that we're working with. This is the quote-unquote formula for integration by parts. It's u dv and then equals uv minus the integral of v du. So they switch. It goes u dv, v du. All right. Okay, so we plug everything in, folks. We've got u dv, that's 7x times 1 over 3x plus 5 dx. That is our original formula that we were trying to find. And now we'll do uv, which is, it's 7x times 1/3 natural log of 3x plus 5. So I'm going to do 7/3 x natural log of 3x plus 5. Is that fair how I did that? I did the 1/3 times the 7 to get 7/3. And then I put the x in front of the natural log of 3x plus 5. And then we're going to subtract the integral of v du. Well, v du, we have 7 times 1/3, so that's 7/3. And then it's the natural log of 3x plus 5. Yeah, dx. Then what, Julie? Yep, then you can take the 7/3 out, which is nice because we have a 7/3 on both of our integrals now. 7/3 natural log of 3x plus 5 minus 7/3, and we're doing the integral of the natural log of 3x plus 5. Okay, and now it's at this point that we're just doing the integral of a natural log function, and we have a formula for that. We have the integral, a formula for the integral of a natural log function. Now, we might just want to consider about the fact that there's an inside function. You know, there's the inside function of 3x plus 5. And we actually did that problem the other day, didn't we? Didn't we do the integral? There it was, the integral of natural log 5z plus 3. That was one of the problems that we did. And then at that point, you would take the solution from that problem, or you know, the similar solution, and it would go right there. So what was the solution from that problem? It's on the answer key right here. This problem, I'm sorry, no, not that problem, but the integral of natural log of, we can just look back at the answer. The integral of natural log of 5z plus 3 was, looking at the answer key, golly, what is it? Z natural log of 5z plus 3 plus 3/5 times natural log of 5z plus 3 minus z. You what? Is that the answer we got?
I don't know. We didn't finish that.
We didn't even finish it?
We did.
No, I thought we did. What was the answer that we?
For 3, we used the W. And then,
Yeah, we did a W substitution at the end.
It was 1/5.
brackets 5z plus 3, natural log of 5z plus 3.
Minus 1/5 5x plus 3.
No.
Let me see.
Don't look at mine.
Don't look at yours? Okay. Yeah, okay, yeah. Yeah, that's totally what I thought. Okay, folks, notice that is the pattern of the formula. I'm going to write it down for you. Writing down exactly what Julie just had, because we can see how this formula works. So using the formula of natural log, it's the integral of natural log is really x natural log of x minus x. The difference here is that we're doing the natural log of what? 3x plus 5? So, everybody ready? We got the formula for the natural log. The integral of natural log of x is x natural log x minus x. The only difference is we're going to throw 3x plus 5 everywhere. So everywhere that you see an x, you're going to put in 3x plus 5. So it's going to be 3x plus 5, natural log 3x plus 5, minus 3x plus 5. So do you see what I've done so far? All I've done is just put in the 3x plus 5 instead of the x. But it's still that formula. But there's one more thing we'd have to do. If we took the derivative of all that, we would be doing the chain rule. And at the end of taking the derivative of all that, what would you have to multiply by? You'd have to multiply by the derivative of 3x plus 5, which is 3. So if I did take the derivative of all this, I would end up with a 3 at the end. I would end up with 3 natural log of 3x plus 5. But I don't want the answer 3 natural log of 3x plus 5. I just want the answer natural log of 3x plus 5. So what would I have to tack on to this whole answer to cancel out that 3? Well, 1/3. And that's it. So this is how we would finish out this problem. We're going to write down the first part because we're already done there. It's 7/3 x natural log of 3x plus 5. And then we're minusing 7/3. And at this point, we're going to use the formula for the integral of natural log. And remember, the formula for the integral of natural log is x, natural log x, minus x. That's the formula. But we're going to plug in 3x plus 5 for all those x's. So it'd really be 3x plus 5, and then the natural log of 3x plus 5. And then you subtract 3x plus 5. But because that whole thing, there's an inner function of the 3x plus 5, we also need a 1/3 factor out front. And that's the end of the problem. What's that?
So wasn't it supposed to get easier?
Wasn't it supposed to be easier?
No, like, I don't know.
Well, for today, the two problems I wanted to do with you today were 5 and 6, and 5 was definitely fairly straightforward. This one was a little more challenging because we utilized the formula for the integral of natural log of x. And yeah, I had some trepidation about this one. I know this one is hard. This one is tricky. Okay, I don't want to say hard, but there's a lot of steps to it. But I still wanted to do it so that you could see the power of doing integration by parts and using a formula from a former integration by parts problem. Julie?
Would it have had them going all the way? I mean, would it be wrong if I took the 7/3 and pulled out the 7/3?
No. No, in fact, you could do a lot of simplification right here, couldn't you? You could pull out the 7/3, and what else could you pull out? I don't know if we can pull out the natural log, because there's one on this term and there's one on this term, but not on that term. Actually, I think that's all you can pull out. You can pull out the 7/3, and then you'd have x natural log of 3x plus 5. And then you'd have minus 1/3 of 3x plus 5. Natural log of 3x plus 5. And minus 3x plus 5. And that would be your final answer. Is that what you were saying, Julie?
Yeah.
Pull out the 7/3? Yeah, you certainly could. Yeah, Nate.
Do you think that if we had this on a test, that would be given, or should we make sure we?
You know what I think I would really like to do for the test is I would like to see you derive this for me. Show me how to derive the formula of the integral of natural log of x. I think that's a good, solid problem. It's actually a rather short problem. It's not overwhelming at all. And for the test, I would definitely give you an integration by parts problem like number 5, but I probably won't give you the problem like number 6. So the problem that we just did, it was a good growth experience, but it won't be on the test. Is that okay? All right. All right, well, folks, we did it. We learned about U substitution. We learned about integration by parts. And now we get to move on and do some application problems. All of the application problems that are coming up are actually really cool. These are really fun application problems using the integral to solve real problems.
Are we not going to do number 7?
We're not going to do number 7. Oh, sorry, I said that at the beginning of class. We're not going to do number 7. And if you all checked your email already, I sent out some email messages the other day that we're not going to do the rest of 3.5b either. So the rest of this packet says 3.5b. We're not going to do this material. On second look, looking at it again, I thought none of this has an application to business. These are not the types of problems that we need to focus on.
If nobody from class, they're just.
Oh, okay. Do you think they want to come in?
Yeah, I
We can bring them in. Just have them do some problems with us.
You can take my seat for a little bit.
Okay, just to warm it up. Okay.
think.
All right, folks. Well, let's go ahead and take a look at that 3.6 packet. And you'll notice that it's asking area problems. Yeah, here we go. Area, volume, and average value. Now, the first thing I want you folks to notice is that in these problems, the only thing they gave was the words. Okay, so on Math AS, all they gave you was the words. They said you want to find the volume of a solid obtained by rotating about the x-axis, the region under the curve, 7 equals x to the 1/7 from 0 to 4. I put this graph on here for us because I needed us to be able to visualize what we were doing. So the graph is not going to be given to you in Math AS. You'll have to pull up Desmos or some graphing calculator, sorry, so that you can actually visualize what they're talking about. Okay, so let's do that together. We want to understand what they're talking about, the volume of a solid obtained by rotating. This is a very interesting set of problems we're about to do. Volume obtained by rotating around x-axis. I was hoping to find some obvious nice pictures. This is an okay picture. That's only okay. Oh, here we go. Okay, here's a nice image of what they're talking about. There we go. What they essentially did here, and I'll draw this one, is they took a very simple graph, namely the function x. So this is just the function mx plus b, and it's simply x. Okay, so it goes to the y-intercept of 0 and it has a slope of up 1, right 1. And what they do in calculus, and actually in machining or 3D printing, is you take the idea of a curve here, and what they say is now rotate it around the x-axis so it comes out of the board and into the board, and it starts this rotation process. And you create a 3-dimensional object by rotating this line around the x-axis. So can you see in that picture how they did that? This line is going to rotate around and around the x-axis, so coming into the board, out of the board, into the board, out of the board, and it's going to create a 3-dimensional cone. So that's what they're talking about. They're talking about taking a line and then rotating it. I really wish that I had, and I should have thought of this before class, a video of that. But volumes by rotation, maybe this has a nice picture. Oh, there we go. Yeah, that's not bad at all. See, they're taking that simple line right there, and then they're rotating it around and creating a 3-dimensional object. Okay, that's a fairly good image. So we all know what we're talking about. You can take any graph and then rotate it around the x-axis and create a 3-dimensional solid, and then say you could print that on a 3D printer, or you could machine it somehow. But boy, it sure would be neat if there was a video. What if I just type in a video? Disk method. I wonder if they'll show something. Bless the Khan Academy. They really don't have
over here. I'm going
best
yeah, the area
visualizations.
Right
that's not that
side
bad.
of this thing, and then pops out the other side. And if this thing was transparent, then you could see.
Can you see that at all?
The back side.
So you can see what they're doing there by rotating it. Maybe if I just go straight to YouTube, type in volume rotation around x-axis. Oh, that's a fun one. Maybe this will do it.
Welcome to area is dv. And there's different ways of doing that. We can get, well,
What is your password?
I didn't know, I mean.
welcome to electron line, and here we're doing our next example of how to find the volume
Well, that's just
created by
pictures.
taking
What
an
the
area defined by two equations. So here we have a straight line, y equals
Well,
x, a parabola, y equals
I'm
x
sorry,
squared.
folks. I don't want to waste our time anymore. I really thought that it'd be a simple thing of finding
Well,
a simulation. Well, instead of video, I did simulation. Ooh, solids of revolution, Desmos. Is it going to show it? It is not. Ooh, okay. This is not bad at all. This is very nice. So, all right, it's not going to get any bigger than that. Where is it? Up there. I'm going to go back so you can see them all. There we go. So you can see that they're taking a line and then they're rotating around to create a solid. Okay, this is not bad at all. This is what I was hoping to show you. I just wish I could make it a little bigger. So here, do I have to reset the website? Why is it? Gosh, they already did them all. So this is fun. It's kind of like you can see how they made a pot or a clay pot or something like that. And they rotate it around. And there's your solid. Does that work? Is that a good animation? Everybody can see what they did? That's what we're trying to do here. Okay, so back to the problem. We would like to take this function, which they just gave us, and we would like to rotate it around the x-axis and turn it into a solid. So everybody go ahead and mirror image that line down below and draw another copy of it. And we want to imagine now that we just turned that into a three-dimensional object, and it's something that you are going to build or create. What does that look like? Like if you just built that, what would it be good for? Yeah, probably just a nice cup. You know, maybe a wine glass or a goblet or a cup of some sort. Of course, then you'd have to drill it out and make it hollow so that you can actually fit a liquid inside of it, but that's essentially what we're looking at. And so what we would like to do in this problem is find the volume of that solid, obtained by rotating about the x-axis, the region under the curve from there to there. So a couple things that we might consider before we calculate would be, what if it wasn't this funky shape? What if it wasn't funky like that? You know, the fact that it starts off here and then kind of curves and then goes up. What if it was just a cylinder, just a simple cylinder? What if, you know, we kind of take this excess amount of material here and filled in the gaps right here, and we just called it a cylinder. So here's my graph again from 0 to 4, and it seems to go up to 1 and down to 1. And do you think that'd be fair? Like if I just mushed that excess material down, it would just be a cylinder going from here to here? Can you imagine that instead? So get rid of the fact that it's slightly wonky shaped, and we'll just make it a constant cylinder. Now, do you think that if I took all this excess material and filled it in right here, would it be at 1, above 1, or below 1? What'd you say? Because there's a lot of excess material here. I'm kind of thinking that's enough material to fill this in and a little more. Does that seem reasonable? So let's say that actually if we smooth this out and just made it a simple cylinder, it would go up to 1.1. 1.1 and down to negative 1.1. And so my first question for you is, what's the volume of a cylinder? How do you calculate the volume of a cylinder? Do you folks remember? All the way back from geometry, you've got a cylinder.
3 pi r.
What'd you say?
3 pi r.
3 pi r? There's no 3 pi r. There is something for the volume of a sphere. So if it was a sphere, That's actually 4 pi r squared, but that's the surface area. If you wanted the volume of a sphere, it was 4/3 pi r cubed. So in general, though, if you want the volume of something, you do the area of the base. So in this case, the area of the base, I'll call it A, capital A of the base. And then the total height for how tall that particular object is. So that's how you find the volume of a cylinder or the volume of anything. You do the area of the base and you multiply by how thick it is or how tall it is. So the volume of a cylinder is the area of the base times the height. Now in this particular case, what's the area of a circle? Pi r squared. The area of a circle is pi r squared. If you wanted the circumference, that would be completely different. The circumference of a circle is 2 pi r. Okay, throwing a lot of different equations at you. This was the volume of a 3D sphere. This was the surface area of a 3D sphere. Now I'm just talking about a circle. The circumference of a circle is 2 pi r, and the area of a circle is pi r squared. So this would be what we're you all writing up in the upper right-hand corner. You can see I did it in my own notes. I just made a cylinder up here. So let's all make a little picture of a cylinder. And the total volume then is going to be the area of the base, which is pi r squared, and then the total height, which is h. So that is actually the formula of a cylinder. Pi r squared times height. Again, knowing how to use this formula, the area of the base is a circle, so it's pi r squared. And then the h represents how tall or how long that object is. So let's try that formula out on this object if we pretend it's just a cylinder. We're going to pretend it's just a cylinder with uniform length and height all the way along. So for the base shape, which is a circle, what's the radius of our circle? We're going to say it's 1.1. And so now we have pi 1.1 squared. And what's the height or the length of our cylinder? 4. So right now, the formula for our volume is pi 1.1 squared times 4. So go ahead and calculate that on your calculator. And we are going to expect that the answer that we get right now should be awfully close to the true volume of this slightly uneven shape that we're about to do. So what is that? 1.1 times 1.1 times pi times 4. And I got an answer of 15.2053. So I'm going to write that down as a guess. The volume should be approximately 15.205-ish. That would be if you just used the standard formula of a cylinder. But we cannot use the standard formula for a cylinder because this is not a cylinder. It's got curves to it. So now we want to consider how would we do this using calculus. All right, so here we go. I need to read along with you. And of course, now my shape is gone. I'm just going to read it. Yeah, I'll just read it along with you. So the first part says, you first slice through the rotated solid at a generic point X and get a circular cross section. What is the area of that circular cross section? So everybody, let's just come to a point right here. And I'm just going to call that point X. I'm not looking at the point 1.5. I'm looking at a generic point X. And then I'll go ahead and draw a line straight up. That would be the radius of this cross section. I'm going to, like, let's say this is made of sausage. I'm just going to cut right through it. And I'm looking now at a cross-sectional slice of this object. I just cut through it. That's a slice. Like I just cut through a sausage. So what is the circular area of that cross-section? You have to imagine taking that circle and looking at it. What does that circle look like? Yeah, it's just a circle whose radius is X. So what is the area of that cross section? It'd be pi radius squared, right? But what is the radius? The radius is an X. X is our location along the X-axis. What's the height of this curve? x to the 1/7 tells us the height at that point. So if we're looking at some point x, the height up here is going to be the height of x to the 1/7. So that's the height that we're looking at, and that would be our radius. So we're really saying the area of the circle is pi x to the 1/7 squared. And that would be the area of that circle for any point x that we choose. So if we choose the point x way over here, it's going to be a smaller circle. If I choose the point x way over here, it's going to be a larger circle that I'm looking at. So you see how depending on where you choose your point x along this continuum, you're going to get smaller circles and larger circles. And this is telling us the area of any one of those circles that you choose, pi radius squared. And how does that simplify? What's x to the 1/7 to the 2? What happens when you raise an exponent to an exponent? You multiply the exponent. So this is x to the 2/7. So that is the cross-sectional area of each slice of that shape. Okay, now they say this makes the volume of the approximating disk with thickness delta x. So what they're saying is take any one of these slices that you just did and give it some thickness. Give it some thickness so that it's actually a very, very thin cylinder, a very thin cylinder. So can you imagine, I previously drew us a cylinder that was quite tall. Well, what if I just made a very thin cylinder? And I said, here's my circle, it's just that tall. What kind of discs look like that? Or what kind of cylinders look like this? A what? Yeah, a quarter, a coin, a nickel, a can of tuna. And what we're really thinking about, or those round batteries that are in some devices. And what we want to do is consider making this volume, this cylinder, what we're going to do eventually is make the cylinder infinitely thin. We're going to make this cylinder infinitely thin, and we're going to chop this thing up into lots and lots of cylinders that are all infinitely thin, and then calculate the volume of all of them and add them together, just like we did at the Riemann sum. So how thick should we make each disk? We're going to make it a thickness of dx. dx represents infinitely thin. So we just chopped up this whole thing into cylinders. Each cylinder is infinitely thin. Each cylinder has a surface area of pi x to the 2/7. And so now we're going to say the volume of each disk or each cylinder is the surface area of the base times the height of that base. And in that particular case, we're saying that the volume is pi x to the 2/7, and the thickness or the height of each cylinder is dx. So we're moving along here. We've got the area, the surface area of each circle, and now the volume of each disk. And each disk is infinitely thin, and we're going to add those all up along the entire length of this object. All right, so you can see the integral that they have prepared for you all the way at the bottom. The integral that they prepared for you was funny, Susanna. It's just a little wild.
You said it was going to be fun.
Oh yeah. Oh, it's about to be fun. I mean, it's already fun. But listen, we're chopping up this object in order to calculate the volume of each slice and then add it all together. So the volume formula that they have for you at the very bottom, the volume of this object goes from 0 to 4, and we know what that means. We're adding up all the volumes of all of these infinitely thin disks from 0 to 4. And the area, I'm just going to write it down once, the area of each disk, which we calculated to be pi x to the 2/7. And then the dx represents the infinitely thin nature of each one. So our volume formula, go ahead and write equals. I suppose I can get rid of some of this now. Is from 0 to 4 of pi x to the 2/7 of dx. So before we finish this integral, I just want to impress upon you that we're calculating a volume. This is actually a volume. this pi x to the 2/7 dx. And just to make sure that's clear, the pi x to the 1/7 squared dx, this is pi r squared dx, which is really pi r squared times height. This is still the formula for taking a cylinder of a certain height and calculating the volume of it. So the pi r squared is the area of the base, and the height is how tall it is. So we really are calculating the volume of a cylinder. It just so happens that we're calculating it slice by slice by slice. Let's do the integral. The integral is actually quite simple. What can we do? What can we do with the pi? Here, we can go ahead and bring the pi outside. So we have pi times the integral of 0 to 4, and this is just x to the 2/7. And so now we do the anti-power rule, which means we do what? Add 1, and adding 1 is really adding 7/7. So that's x to the 9/7. And then you divide by 9/7, which means you multiply by 7/9. So that's our antiderivative, and we're going from 0 to 4. So again, we draw that vertical line to remind ourselves that we're actually going to plug in 4, and then we're going to plug in 0, and we're going to subtract. So then what do we have? We have pi times 7/9 4 to the 9/7 minus 7/9 0 to the 9/7. Well, what is 0 to the 9/7?
0.
Yeah, 0. So that whole part just goes to nothing. And what we really have then is pi times 7/9 times 4 to the 9/7. So that would be 7 pi 9 times 4 to the 9/7. That is the volume of that object. Nate?
Oh, yeah, mine.
Now, the exciting part is typing that into your calculator and seeing how much that is actually valued at.
14.523.
14 point what?
14.523.
All right. Thank you, Mom. So if you type that in your calculator, you get 14.523. And do you remember what our estimate was? Our estimate was 15.2. That's not bad at all. We were really close. In pretending that this thing was actually just a regular cylinder with a height of 1.1, we got an answer of 15.2, and the true answer is 14.5. So at least we know that, we did this all correctly. And that is the actual true volume of this object. What's that? So what'd you say, Julie? That wasn't fun? Well, maybe it's just because it was the first one. Yeah, because there are more. We're about to do more volume problems. In fact, we should specifically now just skip around and do the volume problems. So what's the next volume problem? Yeah, let's go ahead up to number 5. Oh, you're going to love it. You're going to love it. I also said you're going to love it. This one is a good one. That one, I admit, it might have just felt a little uncomfortable because we had never done such a thing before. And hey, at the very least, did you see how many times we did U substitution? Did you see how many times we did integration by parts? We didn't do any of those things. It was just a straightforward integral. The hard part was setting it up. So let's look at number 5. They're saying the same thing. Determine the volume of a solid generated by rotating this function around the x-axis, but only from 2 to 4. Okay, so find 2 to 4. There's 1, and there's 2, and then there's 3, and then there's 4. So we're only going from 2 to 4. So go ahead and draw in a line, and there's that. And so what we have is this thing. And we're now going to envision rotating that around the x-axis, into the board and out of the board. And what does that thing end up looking like? It looks like that. Can you all imagine what that thing looks like in 3-dimensional space? It's if I were to rotate it like this, it would look like that, right? It's like the cap. I just shaved off part of a ball. If that was a big foam ball, I just cut the top off of it. If I were to draw in the rest of the sphere, it would look like this, but all I did was I just cut the top off of a ball. So I suppose that would be like taking an orange and then just cutting the slice off the top of an orange. Okay, so that's the thing we're about to find the volume of. I just chopped off the top of an orange, but it's sideways like that. Okay, well, as before, we want to look at one cross section to find out the area of that circle. So let's just look at the area of the circle at the bottom that we just looked at. I'm going to do that again because I just run all over it. There was my 2 to 4. Comes down here to there. So there's my cross section. So let's start, everybody. Come on over here and write the area of a circle is pi r squared. We need to know the area of the circle. And so what is the radius? How tall is the radius? For any given circle that I might draw on here, how tall is it?
16.
Yeah, it's the square root of 16 minus x squared. It's the function. The function is telling you how tall the circle is at any given point, and therefore the function is telling you the radius of every one of those circular slices. So as I slice through that circle, the radius of each of those slices is given by this function. So the radius is actually the square root of 16 minus x squared. This is exceptionally convenient because what happens when you square a square root? They cancel out. So the area of one cross-sectional circle is pi times 16 minus x squared. All right. Well, we don't want to find just the area of a two-dimensional flat surface. We want a three-dimensional disk. We want each circle that we look at to have a little bit of thickness to it, so that when we're cutting out our slice, there's some thickness to it. And how thick will it be? Dx. So the thickness is dx. And dx ultimately represents an infinitesimal. It's infinitely thin. And we chop that thing up into infinitely many, infinitely thin cylinders, and you calculate the volume of each cylinder and add them all together in an integral. So now that we have our area, let's do our volume. Volume for a cylinder is pi r squared times the height. That is the height of each cylinder. And in this case, the height of our cylinder is the thickness of the cylinder, which is dx. So now we can say the volume of each slice, okay, we're calculating the volume of each slice right here, would be pi 16 minus x squared dx. How's now? Is this slightly better the second time around?
If she says she likes it, can we stop doing
No. No. If she says she likes it, we'll do more. After all, she likes it. Okay, so does everyone see where we got everything from? The area of the circle is pi r squared, and the function was telling us the radius, so we squared the function, we got this. That's the area of each circle that we sliced through. And so the volume is the area of the base times the height, and the thickness of each cylinder is simply dx, so that's our volume. That's the volume of each slice. So how do we find all the slices and add them up? We do the integral from?
2 to 4.
From 2 to 4 of exactly that formula, pi 16 minus x squared dx. And that integral is actually calculating a volume, the volume of that part of the sphere that we chopped off. So what can we do? And take the pi out, so it's just the pi integral from 2 to 4 of 16 minus x squared. And now we just have to take the integral, the anti-power rule. What's the antiderivative of 16?
X.
16x. And then the antiderivative of x squared?
1/3.
Now 1/3 x cubed, because you add 1 to the power, which is 3, and divide by the resulting power, which is 3. And we're going to evaluate that, 16x. We're going to evaluate that expression from 2 to 4. And what is it that we're calculating again? We're calculating a volume. We're calculating the entire volume of the part of the sphere that we chopped off. Well, this is going to be I times 16 times 4 minus 1/3 4 cubed minus 16 times 2 minus 1/3 times 2 cubed. Right? You know what's really silly right now? Like really silly. You look at this, and this is just some sort of like simple arithmetic problem from grade school. 16 times 4 minus 1/3 times 4 cubed. I mean, are you kidding? This is what students in like 8th grade get. And look at that. That's the end of our calculus problem. The end of this calculus problem is just multiplying and dividing and raising the powers and adding and subtracting a whole bunch of numbers. I mean, it's almost laughable that the end of a calculus problem should be such basic arithmetic. So what, did you all just type all that in your calculator? 16 times 4 minus 1/3 times 4 cubed. So that part was 42.6 repeating. And then 16 times 2 minus 1/3 2 cubed. That part was 29.3 repeating. So then we subtract 42.6666 minus 29.33333. That's 13.3 repeating times pi. Which is what? Times pi. The final volume is 41.8879. By the way, did they give us any units? Is that inches cubed? Is it centimeters cubed? Is it meters cubed? We have no idea because they didn't tell us anything, did they? They just said determine the volume of the solid generating by rotating that function about the x-axis between 2 and 4. So we could say anything. We could say it's inches cubed or centimeters cubed. We don't know. By the way, the answer is 41.88. Was that the answer? Oh boy, 41.8879. It sure was. How exciting. Was our first answer correct, by the way? Yeah, 14.52. That was on the answer key as well. Okay, is there another solid? There is. Let's do number 6. Or, yeah, we should totally do number 6. And then we'll take a break, and then we'll come back and try a different type of problem. Okay, so what does the problem say? Find the volume of the solid obtained by rotating the region bounded by 2x squared. So you all see 2x squared? That's this one, 2x squared. Go ahead and label it in. This is the function 2x squared. Between x equals 3, so that's that vertical line, and x equals 4, that's that vertical line. And we're going to take that thing and rotate it around the x-axis. So what does that shape look like? Yeah, it looks weird, doesn't it? If I were to attempt to draw that, it would look like that. Now, is that super weird? No, it's not super weird. Okay. Mary says it's super weird. Okay, that's what we're rotating. Is that a fair interpretation of what that should look like? If we rotated it? So we want to know what's the volume of that thing. So, keeping in mind that we want to do first the area of one cross section. So we would turn that into a circle, and we want to know the radius. And how tall is the radius? The function 2x squared. So we can start. I would walk our way through it. Area of a circle is pi r squared. The radius in this case is 2x squared squared. Right? The radius is 2x squared. It's pi r squared, so you square that. And the area of one circular cross section is 2 squared is 4, x squared to the squared is x to the 4th. So 4 pi x to the 4th. Is that what everyone got? That's the area of one circular cross section. And then we want to give each circular cross section some thickness. We want to give it some thickness so that we're actually calculating a volume. And how thick is it? Dx. The thickness of each slice will have a thickness of dx. So now we can say the volume is pi r squared times height. That was our original formula. And so the volume of each slice will be 4 pi x to the 4th dx. And so now we just want to add up all the slices. And where are we adding up the slices between? Between 3 and 4. So that's our integral. The integral is from 3 to 4 of 4 pi x to the 4th dx. What do? Then bring up the 4 pi from 3 to 4 of x to the 4th dx. And then the anti-power rule of x to the 4th?
1/5 of x to the 5th.
Yeah, we add 1, so that's x to the 5th. Divide by the resulting number, that's 1/5. And we're going to go from 3 to 4. So leaving the 4 pi out front, that would be 1/5 4 to the 5th minus 1/5 3 to the 5th. Plugging in the 4 and then the 3 and then subtracting. So again, more basic arithmetic. 0.2 times 4 to the 5th. That's 2 minus 0.2 times 3 to the 5th. 121.5, which is 4 pi times 83.3. Did Nor get 1046.7786? Sure. The answer is, wait, what number was that?
6.
6? 1962. That's not what I got. 1962 they got. 2x squared from 3 to 4. Good. What's that?
I got 610 something. When I do 4 to the 5th to the 1/5, that's 204. Oh yeah,
Oh, well, let's see here. Well, that's definitely 4 pi x to the 4th and then 1/5, all that.
When I
So-
do 3 to the 5 to the 1/5, I get 48.6.
Oh, so, oh, well, then that would make a difference. 1/5 times 4 to the 5th, 204.8, and then 1/5 times 3 to the 5th, 48.6. Thank you. That's 48.6. Oh, that'll make all the difference. 48.6, and then when I subtract those, minus 204, I get 156.2 times 4 pi. Oh, good. 1962.867. Okay, I'm sorry. I made a mistake in the basic arithmetic. Here I am sitting up here telling you how funny that the end of a calculus problem is basic arithmetic, and what did I get wrong? The basic arithmetic. Okay, folks, you can see that number 7 is also a volume problem, but I'll leave that one for you folks. All right. Now that leaves us a few problems to do that are completely different. So that's it for the volume problems. Now, as I said, I'm just going to ask you one more time. By the end, was that okay?
Yeah.
Made a little more sense? Now, that first problem was a bit of a doozy. All right, folks, let's take a break. It's 11:17. Let's start again at 11:27.
no hemos lentes.
It's cold in here.
Sounds rough. It wasn't like, just, I don't know. You made it seem like it's gonna be a lot harder.
Which part?
All of it. Like that whole one.
Well, yeah, I think the first problem was rough because it was the first time we did it, and then I probably could have streamlined that. But I mean, by the list problem, was it much easier? Okay, good. I don't get it. Where's the volume?
Remember to the next one we're working on? Remember to the next one we're working on?
Yes.
Hey. I'm doing good. On break from class.
Oh, no wonder.
Okay, I'll let you know when I get here. Thank you. Yeah, I don't have time for that, but I should be home. I love you. Yes, I'll call you later.
That was very sweet of you, Julie.
That's my husband's family.
So is it gonna be cold like this?
Oh, year? Is it next semester?
Yeah.
I don't know. It's definitely gonna be cold like this until March, I'd say.
Oh my gosh.
You don't like it?
Even going outside isn't warming up because it's cold.
Well, it's really nice outside right now,
No,
actually.
it's beautiful out there,
Yeah.
but we were coming from a cold room and going outside.
Yeah.
I don't like coffee with you.
I wouldn't mind sitting, outside, having some coffee.
Oh, coffee or maybe hot chocolate? Mm.
Or I combine the two.
Yeah. Oh, yeah. I always combine the two. Whenever I go to Circle K, I get coffee and I fill it halfway with hot chocolate.
Okay, I'm not the only person that does it. My husband laughs at me for it.
I still think we should bring in a coffee making device in here so that we could all make coffee. That'd be awesome.
Or a heater,
Or a heater.
one of the two.
All right, we're ready to go. So we're changing gears. We're not going to do any more volume problems. Instead, we'll do some area problems. I think you'll really like this one. They're really fun. These are great problems. So it says here, Farmer Jones and his wife, Dr. Jones, decided to build a fence in their field to keep the sheep safe. Since Dr. Jones is a mathematician, she suggests building the fence described by this. So we're going to go ahead and trace it out. She wants to build a fence in her yard that looks like that. That makes no sense. But that's what they want. That's the fence. And so there's going to be little sheep in there.
Look like little clouds.
It's a sheep.
That was raining.
Maybe it's like, okay.
There, it's a sheep. Obviously. So this is the area that we want to find. Right in.
Sheep, don't forget that.
And we finally get to the point which I was describing on the first day of class, that what does calculus do? Well, the derivative is the slope of a curvy curve, and the integral is the area of a curvy shape. So here we are, finally finding the area of a curvy shape. A very curvy shape. There's not even a flat part to it, is there? So if we want to find the area, they give us a formula. It's up at the top, but my screen doesn't really show it very well. It says that the area between two curves is simply you subtract them. So let's just write that out together. The area between two curves, where f of x is the top curve and g of x is the bottom curve, if you want the area trapped between those two curves, you just do the integral of f of x minus g of x. Does it make sense that that would be the formula for the area between them, that you subtract? It does make sense, because what you're really looking at is the height. What is the total height of each part? Because as before with the Riemann sum, what are we doing? We're cutting it into rectangles, right? We're cutting it into infinitely many, infinitely thin rectangles. And the height of each rectangle is given by the top part minus the bottom part. And in that way, you cut this whole shape into infinitely many, infinitely thin rectangles, and you add them all up, and that's the integral. So in this case, what would our integral be? We're going between where to where? We're going from -2 to 2. Now, is that obvious that they actually do meet at 2? Do we know that, or does it just look like it? It looks like it. Do they really meet at 2 and 2? How do we find out where this curve, x squared plus 12, meets this curve, 4x squared? You would have to set the two equations equal to each other. If you wanted to be really sure that they really did meet there, you'd say 4x squared equals x squared plus 12. You'd say, hey, where do those two curves meet? So you set them equal to each other, move the x squared over to the left, and you get 3x squared equals 12. And then you have dividing off the 3, and you get x squared equals 4. And now you can see what we assumed to be true, which was that they meet at plus or minus 2. But now at least we know for sure, and we weren't just assuming it from the graph. So sure enough, we're going to do our integral from -2 to 2. And the top function is x squared plus 12. And the bottom function is 4x squared. And that's our integral. Oops, from -2 to 2. There we go. And that is going to tell us the area of the curvy shape. Can we simplify that integral a little bit? We can combine like terms at least, right? 1x squared minus 4x squared, that's -3x squared plus 12 dx. Well, this is a pretty straightforward integral to calculate. You can all go ahead and keep doing it at your paper. Nate?
How do we know to use x squared plus 12 first rather than?
Because you do the one on top. X squared plus 12 is this curve up here. You can tell because it's x squared plus 12. It's a parabola that has been shifted up 12. Whereas 4x squared goes through the origin. And so that's the curve down below. Yeah, good point. It's the top function minus the bottom function. Nate, thanks for asking that. That wasn't obvious. F of x minus g of x, because you're doing the top function minus the bottom function. So we go ahead and finish our integral. And so the anti-power rule, that'd be x cubed, and then divide by 3, so that's really just -1x cubed plus 12x. And we're evaluating from -2 to 2. And so that gives us -1 2 cubed plus 12. Wait, that's 12x. 12 times 2 minus -1 times -2 cubed plus 12 times -2. Once again, I'd like to point out the hilarity that the end of a calculus problem is basic arithmetic. Does anyone else find that interesting or funny, or is it really just me? There's a certain irony here. There's a certain irony here that here we are working on this advanced calculus, and the end of problem is a PEMDAS situation, where all we're doing is, please excuse my dear Aunt Sally, doing a bunch of exponents and such. It's wildly fun. So what do we get? That's -8 plus 24, and then that's -8, positive 8, minus 8, and then that's -8, that's plus 24. So it's 24 minus 8 is 16, plus 16 is 32. Did everyone get 32?
No.
Mm. Oh, you're just not there yet, okay. Something else neat that I'd like to point out. We're doing this problem where we have the graph x squared plus 12, and we have the graph 4x squared. And we're looking at the area trapped between them. Bring this up a little bit. There we go. So we've got this area. Okay, can you all see it over there? The area trapped between the red curve and the blue curve, which looks like a big happy face, like a clown's mouth. And yet, when I subtracted those two functions, what did I get? Negative 3x squared plus 12? Negative 3x squared plus 12. What we're saying is that the area between the blue and the red curve has the same area as that area underneath the green curve. So can you imagine it? This curve right here, the negative 3x squared plus 12, has the exact same area as the area that we were considering, which is kind of funny because it's like taking a clown face. Do you see the clown face and all of his teeth? He's smiling at you there. And we're taking that happy face and doing what to it? Turning it down into a sad face. And yet the area underneath that curve is exactly equal to the area under that curve. And that's very interesting that those two curves, those two areas have the same area. It's almost like you take that clown face and you melt it down. Can you see it? Can you see you taking the two corners of that clown's cheeks and pulling it straight down and turning that happy face into a frowning face? Because those two areas are truly the same. That's pretty interesting. Okay, did everyone get 32?
Yeah.
All right, let's keep going. The next one is very similar. They want to find the area. They want to find the area between those two curves. Now, folks, once again, I did this for you. I put all these graphs on this piece of paper so that you could all visually see what we're doing. When you're sitting at home doing Math AS, is there going to be a graph given to you? No. So you'd have to go onto Desmos or something and graph it yourself. Of course, do you even really need to graph it? We already know that the formula is you go from A to B of f of x minus g of x. So you might not even have to visualize it except to know which function is on top. You know, because f of x has to be the function on top, and g of x has to be the function on bottom. So if you didn't graph it, how would you know which one was on top? You might not. So you definitely should graph these things to see what they look like. And so what is the function on top? The function on top is the straight line, 5x. The function on bottom is the parabola, 9x squared. And so we're going to do the integral 5x minus 9x squared. From where to where? From 0 to what? We're definitely going from 0, right? Because don't the curves meet at 0? They look like it, but where do they intersect up here?
Is that 0.5?
It appears to be 0.55, but where is it really and how do we know? You would technically have to set the two curves equal to each other, right? If you actually want to know for sure where those two curves intersect, you need to say, okay, when do those two functions equal each other, set them equal to each other. And then, in fact, what you need to do now, since there's an x squared term involved, this is a quadratic. So we'd move the 5x term over to the right, and we get 0 equals 9x squared minus 5x. Now what can we do now? We can factor out an x. So we have x times 9x minus 5. And the zero product rule states that if you have two things multiplying to equal 0, one or both of them has to equal 0. So we set both of them equal to 0. We say, well, either x equals 0, which is the obvious one that we knew by looking, that the two curves met at 0, Or you know that 9x minus 5 has to equal 0, which tells you 9x equals 5, which means x equals 5/9, which is 0.55555 repeating. So that wasn't totally obvious that the answer was going to be 0.55555 repeating. I think looking at the graph, we might have all just assumed that it was 0.55. So what's our actual limit of integration? From 0 to 0.5 repeating. Which you could also write in 5/9. 5/9 might be better. Okay, so now we do our integral, doing the anti-power rule. So x to the 2 5/2, because I added 1 to the power and divided by 2. And then I add 1 to the power and divide by 3. And I do the limit of integration from 0 to 5/9. I just love when an integral is done from 0 to something. Why is it so exciting to do it from 0?
You don't have to worry about the 0 part.
Yeah, you don't have to worry about the 0 part. All we really are doing is plugging in the 5/9 part, and then we're subtracting, plugging in 0, but when you plug in 0, all that goes to 0. So all we really do is plug in 5/9. So it's 5/2 times 5/9 squared minus 3 times 5/9 cubed. I cannot contain myself from saying it again. Do you see the problem at the end of this calculus problem? It's just arithmetic. It's a bunch of fractions being squared and cubed and multiplied and subtracted. I can't get over it. This is what they study in 7th grade, and maybe even before that. Can you imagine showing up in a 7th grade classroom and saying, guys, take this seriously. You're doing calculus. I mean, that would sound like you're just messing with them, right? They wouldn't even believe you. Okay, so what's the answer? 5/2 times 25/81 minus 3 times 125 729, which is 125, 160 seconds minus 375 729. Oh, I don't even want to keep going. I'll just use a calculator. What did everybody get with a calculator? 125 divided by 162 minus 375 minus 729, provided I even did all that right. Ooh, I don't know. What was the answer? Oh, I did that wrong. Ah.
0.25720.
Yeah, okay, that's what I got as well. And as a fraction, it turned out to be 125/486. But that was the answer, right? 0.25. Oh, 125/486. That was the answer at the back. What do you think about finding the area underneath curvy curves? Pretty straightforward application, finding that area. So let's see here. I don't think we'll do the next one. Number 4. It's another area problem. You've got the top curve, the bottom curve, and you're subtracting. You might want to go ahead and take your pencil, though, right now and shade in what's the area we're actually finding. They said sketch the region enclosed by e to the 2x, e to the 5x, and x equals 1. So which one of these functions is e to the 2x, and which one is e to the 5x? Which one grows faster, e to the 2x or e to the 5x? E to the 5x. So this curve is e to the 5x. This curve is e to the 2x. And we're looking at the area here. Right? Isn't that the area that we're looking at? Just that area.
When you subtract e to the 5x minus e to the 2x, is that just, oh wait, no. Would that be, you wouldn't do e to the 3x?
Correct. Why not?
Those are different.
Yeah.
Exponents you
I
can
mean-
combine.
Yeah, I mean, imagine doing this. Would x to the 5th minus x squared be x cubed? Definitely not. I mean, you could factor out an x squared, and then it'd be x cubed minus 1, and you might be able to do something similar here, but I don't think I would even try. You would just go ahead and do the integral. I'd be happy to remind you folks, what's the antiderivative of e to the 5x? It's like the power rule, but different. You don't add 1 to the number, but you still divide by that number. So the antiderivative of this, okay, I said I wouldn't do this problem, but we're already practically done, right? We subtract the top one minus the bottom one. The antiderivative is 1/5 e to the 5x minus 1/2 e to the 2x, evaluating from 0 to 1. That's well worth memorizing, folks, that the antiderivative of e to the something, in fact, you can write it down, the antiderivative of e to the nx is 1 over n e to the nx. It looks a lot like the anti-power rule. The anti-power rule of x to the n is actually x to the n plus 1 over, sorry, and then divide by n plus 1. They look similar, but they are quite different. Okay, I'm not going to finish that problem. Let's move on. Okay, the last couple problems are 8, 9, 10. You know, thinking about today, and especially Susanna, thanks for your honest feedback earlier. I probably could have done these problems in a different order. I could have done the area of the curvy curves first, because that's nice and easy. Now the average value problem is also nice and easy, and then end with the volumes after like warming up, right? Probably we could have gone in a different order. Okay, so folks, this is a really fun problem. Oh no, I keep saying it. I'm sorry. It is a really fun problem. It says, find the average value of the function on the interval from 1 to 4. So everybody note the values 1 through 4. And you can see the curve goes up to there. And so your function is taking on values from, say, what? Where does the function begin? I think it starts at 6. And then it climbs all the way up to what? 96. So this parabola is just the parabola 6x squared on the interval from 1 to 4. It starts at a value of 6, and then it starts climbing. 6, 10, 20, 30, 40, 50, 60, 70, 80, 96, and that's where it ends. So our function is taking on the values anywhere from 6 to 96. How did I get the number 6? Yeah, I just plugged 1 into the formula, right? 6 times 1 squared is just 6. And then how did I get the 96? 6 times 4 squared is 6 times 16, which is 96. But the question is, what's the average value? Okay, and so this is the fun part. I want you to imagine that this shaded area down here, all that area, you're going to take it and say that it's made of butter or ice, and you're going to melt it. And it's going to melt into a liquid and fall down and create an average amount of substance. Does that appear to be the average right there? If I took all this substance and put it down here, would that be the average value? Again, in your mind, I want you to imagine that it's a substance that can melt, and it falls down according to gravity and takes on an average amount of liquid, filling that whole space. I don't know. You draw it. What do you think the average is? I think I'm going to make it a little lower, actually. I think the average would be around there. That still might be too high. That's 40. What, do I have any takers on whether it's more than 40 or less than 40? You're going to say less than 40? Just barely less than 40?
Oh, okay.
Okay, I've got a guess for 39. What were you saying, Julie?
I was just saying leave it.
We also leave it.
Oh, just leave it at 40?
Yeah.
Oh, okay. Well, yeah, so it's somewhere right around there, right? So how do we find the average value? Well, what would you do to find the average value? You, what?
No, I thought you were asking.
Yeah, yeah.
Find the area and divide by 4.
Yeah, exactly. Well, 4? Yeah, you find the area, right? So you first find the area, and we already know what the area is. The area is the integral from 1 to 4 of 6x squared dx. That's the total area. And then what you'd want to say is create a rectangle that has the same area, and what we don't know is the height of that rectangle. You know, we're saying create a rectangle that has the same area as the integral. And what I know for sure about this rectangle is that the height is h, that's my unknown h, my unknown average value. But my width is definitely 3, but we're going to call it 4 minus 1. The width is 4 minus 1, which we know to be 3. So as a quick and handy formula here, we're saying take the area of the integral and set it equal to the area of a rectangle, which is length times width. So the length would be 4 minus 1. No, sorry, that would be the width. The length is the height, which is h, and then the width is the 4 minus 1. And what we're really interested in is the average value, or the height. So how do you solve for height? You simply divide off. That's 1 minus 4. Oh my gosh, guys, I'm sorry, that's 1. No, it's 4 minus 1. It is 4 minus 1. You would just divide off the 4 minus 1. And the average value is simply the total area divided by 4 minus 1. And so what we do here, since that's the area of the whole thing, the average value is 1 over 4 minus 1 times the integral from 1 to 4 of 6x squared. Because we're dividing by the width in order to get the height, and that will tell you the average value. By the way, folks, maybe you already looked at the formula up there, but do you see the formula?
Oh, awkward.
You can barely see it. The formula is 1 over b minus a, the integral from a to b of your function. That's telling you the average height of that function over that interval. And that's how they arrived at it, because you take the area of the curvy shape, and then you say, I want a rectangle that has the same area. And since you already know the width of the rectangle, you can easily solve for the height of that rectangle, and that's your average value. Okay, so what was the answer? The antiderivative of a 6x squared, you add 1, so that's x cubed, divide by the resulting 3. And we're going to go from 1 to 4. But then when we're all done, we're going to multiply by 1 over 4 minus 1, which is 1/3. So it's 1/3. 6 over 3 is 2. So that's 2 times 4 cubed minus 2 times 1 cubed. So that's 1/3 times 4 cubed is 64 times 2 is 128. Minus 1 cubed is 1 times 2. And so that's 1/3 times 126. Oh, and 3 actually goes into that. Oh, 42. It was actually 42. I was wrong to suggest that it looked like less than 40. It's actually more than 40. The average value happened to be 42. Folks, I realize class is just about over. I just want to point out, we only did one of these problems, but they're pretty straightforward. And so I think you can now go ahead and go finish problems 8. 9. No, I'll do 9 and 10 with you next time, okay? Yeah, I'll do 9 and 10 with you next time. Okay. Well, I guess we're done.